Over 4 videos, we've built every piece of a GAN, the generator, the discriminator, and the adversarial training game. Now it's time to see everything come together in real code. We'll walk through a complete working GAN implementation in PyTorch, from model architecture to training loop to generated images. Let's code a GAN from scratch. First, let's set up our configuration. We define all hyperparameters in one place. The latent dimension is 100, which is the size of our noise vector z. Batch size is 120, and we use the Adam optimizer with a learning rate of 0.2. This is the GAN paper's recommendation. Notice beta 1 is set to 0.5, not the default 0.9. This is crucial for GAN stability. We also set up label smoothing. Real labels are 0.9 instead of 1.0 to prevent the discriminator from becoming overconfident. Now the generator, the heart of image creation, it takes our noise vector z of 100 numbers and transforms it into a 28 by 28 image. The first layer is a dense layer that maps z to a 7 by 7 feature map with 256 channels. That's our starting spatial resolution. Then we use two transpose convolution layers, contranspose 2D, each doubling the spatial size. 7 becomes 14, 14 becomes 28. Batch normalization and ReLU after each layer keep the gradient stable. The final layer has no batch norm, just a tan activation that squeezes output to -1 to 1. This matches our normalized input images. The discriminator is the opposite architecture. It takes an image and compresses it down to a single probability. Two convolutional layers with stride to shrink the image. 28 becomes 14, then 7. No batch norm on the first layer. This is important for D-stability. We use leaky ReLU with a slope of 0.2 instead of regular ReLU. This prevents dead neurons in the discriminator. The final layer flattens everything, passes it through a linear layer, and applies a sigmoid, giving us a probability between 0 and 1. Real or fake? Before the training loop, we set up three critical pieces. First, the data Fashion-MNIST with 60,000 clothing images normalized to -1 to 1 to match our 10 output. Second, the loss function binary cross entropy, which measures how wrong our predictions are. And third, two separate Adam optimizers, one for the generator, one for the discriminator. Each network has its own optimizer because they train independently. We also create a fixed noise vector that we'll use throughout training to visualize progress. Same Z improving G. Now the adversarial game begins. Phase 1, train the discriminator. We take a batch of real images and create smooth labels 0.9 instead of 1.0. The discriminator predicts and we compute the BCE loss against the real labels. Then we generate fake images by sampling noise and passing it through the generator. The generator is detached here, its gradients are frozen, the discriminator predicts on the fakes, and we compute loss against labels of 0.1. We add both losses and backpropagate, but only the discriminator's weights update. The generator doesn't change in this phase, it's being held still while the discriminator improves. Phase 2, the generator's turn. We sample fresh noise and generate new fake images. These go through the discriminator, but here is the crucial trick. We label these fakes as real with a label of 0.9. Why? Because we want the generator to produce images that the discriminator believes are real. When the discriminator says this is fake but our target says real, the loss is high. That high loss creates strong gradients that flow backward, but only through the generator's weights. The discriminator is frozen in this phase. This one-liner criterion, pred, fake, real labels, is the entire adversarial signal that drives the generator to improve. Let's understand exactly what the loss is measuring. Binary cross entropy for the discriminator has two terms. For real images, negative log of d of x, this is maximized when d correctly outputs 1 for real data. For fake images, negative log of 1 minus d of g of z, maximized when d correctly outputs 0 for fakes. The generator's loss is negative log of d of g of z. It wants d of g of z to be close to 1. When the loss is low, the generator has fooled the discriminator. Together this forms the famous Minimax equation. The discriminator tries to maximize v, the generator tries to minimize it. Two players, one objective function pulling in opposite directions. This tug of war is what creates the learning. Now let's see why this minimax loss actually works geometrically. Imagine all 28 by 28 images as points in a massive 784 dimensional space. Real images, shoes, shirts, bags, don't fill this space randomly. They lie on a thin curved surface, a manifold embedded in that high dimensional space. The generator maps from a 100-dimensional latent space onto this manifold. Each point z maps to one image g of z. Now here is the key insight. The loss gradient, the direction the loss decreases fastest, acts as a tangent vector on this manifold. When g's output is off the manifold, meaning the image looks fake, the gradient points toward the manifold surface, pulling g of z closer to real images. As training progresses, g of z moves along the manifold, sliding across valid image space. The tangent vector keeps g's updates on the surface, not flying off into noise. This is why smooth latent space walks work. The generator learns the geometry of real images. What does healthy training look like? In the beginning, D-loss drops quickly, it easily spots fake images. G-loss is high, its fakes are terrible. As training progresses, G improves and D's job gets harder. D-loss starts rising. G-loss drops at equilibrium, both losses oscillate, neither network dominates. D accuracy hovers around 50%, it literally cannot tell real from fake. But watch out, if D becomes too strong too fast, G's gradients vanish. The loss becomes flat and G stops learning. And if G finds one image that fools D, it may produce only that image, mode collapse. This adversarial balance is delicate, which is why we need the stability tricks. Let's watch what the generator produces over training. At epoch 1, it outputs pure noise, random pixels with no structure. The discriminator rejects everything with 99% confidence. At epoch 10, basic shapes emerge. Blurry outlines of shoes and shirts start to appear. By epoch 25, the images are clearly recognizable. You can see t-shirts, sneakers, bags, textures and shading develop. At epoch 50, the generator produces clean, sharp clothing items that could fool a casual observer. The discriminator's accuracy has dropped to around 50%. The adversarial game has reached its equilibrium. Gen training is notoriously unstable. Let's cover the biggest pitfalls. First, mode collapse. The generator finds one output that fools the discriminator and keeps producing the same image over and over. You will see identical shoes in every grid cell. The fix: use mini-batch discrimination or unrolled steps so D sees the diversity of outputs. Second, vanishing gradients. If the discriminator becomes too strong, D of G of Z goes to 0. Log of 0 is negative infinity and the gradients vanish. The generator receives no useful learning signal. Third, training oscillation. The losses bounce wildly without converging. This usually means the learning rate is too high or the architecture is unbalanced. Monitor both losses. If one explodes while the other flatlines, something's wrong. Here are 5 battle-tested stability tips, all shown in code. 1. Batch normalization in both G and D except D's input layer and G's output layer. 2. Use leaky ReLU in the discriminator with a slope of 0.2. Regular ReLU causes dead neurons. 3. Normalize all input images to -1 to 1, matching the 10 output range. 4. Label smoothing. Use 0.9 for real and 0.1 for fake instead of hard 1 and 0. This prevents D from becoming overconfident. And 5. Use Adam with a learning rate of 0.0002 and beta 1 of 0.5. These specific values come from the DC GAN paper and they work. One of the most magical results of a trained GAN, the latent space walk. We take two random noise vectors Z1 and Z2 and linearly interpolate between them. The code is beautifully simple. We create a series of alpha values from 0 to 1, then blend Z1 and Z2. Each blended vector produces a unique image and the transitions are smooth. One clothing item gradually morphs into another. This proves the generator hasn't memorized the data, it has learned a continuous, meaningful representation. The latent space is a universe of infinite fashion designs. And that's a complete GAN coded from scratch. Over 5 videos we've understood every component, every equation and now every line of code. The full source code is available on GitHub, model, training loop and generation scripts. Clone it, run it, experiment with it. GANs opened the door to a new era of generative AI and now you can build one yourself. Stay curious.